Hello students, our topic for discussion is self-induction, combination of inductors, energy stored in inductor, self-inductance of solenoid and energy stored in the solenoid. So, what is self-induction? सबसे पहले self-induction क्या होता है? हमारे पास एक इंडक्टर कॉइल है. ये कॉइल का करेक्टरिस्टिक्स है कि when the current flow through the coil, when the current decay or grow through the inductor coil, it gives the induction to oppose this growth and decay of current, that is called the self-induction. This is the characteristics of a single coil. When we say we have the coil, we have the source and we have the tapping key here. When the current grow, it gives the induction. When the current decay, it gives the induction, because when there is a growth and decay of current, there is a change of flux of this coil. That is, this induction is called the self-induction. And we can say this flux is proportional to current, and we have the constant that is called the coefficient of self-induction, that is L. According to Faraday's law, induced EMF is rate of change of flux. In this case, we can say the flux is Li. So, induction minus L di upon dt, or we can say in magnitude we leave this negative sign and we got that this coefficient of self-induction is E di upon dt. So from here the coefficient of self-induction is flux upon current, and from here the coefficient of induction is E upon di upon dt. How to measure this? In SI system, the units for self-induction is called Henry, Henry, that is H Henry. And how we define this Henry? L is equal to E di upon dt. We can say 1 Henry, 1 volt, 1 ampere per second. So 1 Henry is the self-inductance of a coil when the rate of change of current of 1 ampere per second gives the induced EMF for 1 volt. Then this induction is said to be 1 Henry. From here we also define it. 1 Henry can be 1 Weber per ampere. This is also the 1 Henry self-induction. So, self-induction, induced EMF in a coil due to the change in magnetic flux of the coil, that is self-induction. इसे inertia of electricity कहा जाएगा. क्यों? Inertia is the opposition offered to the change. Similarly, induction in the coil is opposition to the growth and decay of the current in the coil. So it is called inertia of electricity. It is called back EMF. So this is self-induction. Next one is combination of inductors. How we give the combination? As we know, the combinations are two types. We say series combination and we say parallel combination. So when we considering the series combination, in series combination we have the current is considered as same and the induced EMF is considered as different, E1, E2. Then how we write this? So let we remove it first, then we describe this combination. Let me erase it. So let's start this. here E1 minus L1 di upon dt, E2 minus L2 di upon dt, and the total E1, E2, if we consider as series combination. So di upon dt, this is minus L1 di upon dt minus L2 di upon dt. What we got here? What we got from this equation? That series combination is L1, L2. And then we're considering it as a parallel combination. L1, L2 induced EMF. The current is I1, I2, and we can say it the parallel combination. So here, what we have here, we have the induced EMF same. L1 di1 upon dt. So di1 upon dt is E upon L1. Similarly, di2 upon dt is E upon L2. Similarly, if we say the total current is E upon LP. So here we have the sum of it. Here we have the sum of the currents. That is di upon dt, di1 upon dt, di2 upon dt, and when we put the values here, what we got, ELP, EL1, EL2, what we have the result? LP, L1, L2. So when we are considering the series of combination for it, we have this combination, and when we have considering it, we have this parallel combination. So our combination of inductor is series and parallel. Now the next is energy stored in an inductor. When inductors current flow through the inductor, it gives the induction, induced EMF, and that induction will oppose the growth of current. So source has to do the work done to maintain the current, and that current is called the energy stored in the inductor. That current is energy stored in the inductor. How we calculate that energy? That means work done, EI dt, and E magnitude form is di upon dt. So this work done, L di upon dt, I dt, dt cancel, work done is Li di. Then how we get the net work done? Net work done is the, when we integrate it 0 to I, what we get, that is I square by 2, 0 to I, and here we can say that the work done is half Li square, and this is the energy stored in the inductor. And remember, this energy stored is in the form of magnetic field. Remember it. When the source of EMF do the work to keep the current flow in the inductor, there must be the energy stored in the inductor, and that energy stored is in the form of magnetic field. Okay. Then the next is self-inductance of a solenoid. How we calculate the self-inductance of the solenoid? For that, we consider a long solenoid having the length L. First we erase this. Then we start the next one. That is solenoid of length L, number of turns per unit length is N, and I is the current flowing through it. Then the magnetic field, mu naught Ni. That's, we know it. We have to derive it in the magnetic effects of current. So B is mu naught Ni. Now, magnetic flux linked with one term, that is magnetic field into area. When we say that A is the area of it, means mu naught Ni टोटल फ्लक्स, ये तो एक टर्न का है, हमारे पास तो n नंबर ऑफ टर्न्स पर यूनिट लेंथ हैं, तो टोटल फ्लक्स इज phi, दैट इज म्यू नॉट Ni A into NL per unit length, total number of turns. So this is mu naught N square IAL, and as we have the definition, this is Li. Then how we write this? From this and from this, we got the self-inductance of this long solenoid is mu naught N square AL. This is the self-inductance of the long solenoid that is considered as this. Here we have the steps. First we write the magnetic field, then we have the one turn flux, then we have the total flux, and then we have the definition, and when we equate them, we got this magnetic, this self-inductance of a solenoid. Then our today's last part, that is the energy stored in the solenoid. Now we have the term energy stored in the inductor, that we have finished energy stored in the inductor. I don't erase these two terms, what I require in this topic, that is energy stored in the solenoid. So for the solenoid, I have this induction, and for the solenoid, this is the magnetic field. From here, current is written as B upon mu naught N. And as we know here, energy stored in inductor, the work done by the source of EMF to maintain the current in the inductor, we have the formula that is half Li square. So let's do it. ये वैल्यू और ये वैल्यू हम इसमें फिल कर देंगे एनर्जी स्टोर्ड इन सोलेनाइड को पढ़ने के लिए. बी स्क्वायर म्यू नॉट स्क्वायर एन स्क्वायर. When we put this value, so here we cross it, here we cross it, then what we got here, now the energy stored is B square upon 2 mu naught AL. B square upon 2 mu naught AL, and this is the energy stored in the solenoid, and this energy stored is again in the form of magnetic field. Here we have one more specific term that is represented as small uv, and this is called the magnetic energy density, and it's a very important term, magnetic energy density, and that is written as the energy stored of solenoid upon volume of the solenoid. This is called energy density. And what we got here, when we put this value divide by the volume, this value when divided by the volume, this energy density come out to be V square upon 2 mu naught. So this is called the energy density of the solenoid. Energy stored in the solenoid in the form of magnetic energy, and when it divide with the volume of the solenoid, we have the energy, magnetic energy density, that is B square upon 2 mu naught. So here we discuss these all topics. Thank you.